Okay, we're back. So today I want to look at the concept of a radical versus a surd. Before we start with the idea of a radical, I think it's important that we understand exactly what a rational number is. We already kind of talked about rational numbers maybe in the past, dealing with indices and rational indices, but a rational number is a number that can be written as a fraction. That's all that it is. So I think sometimes it's best when we deal with things like this to look at an example. So the number three can definitely be written as a fraction. It is the exact same thing as 3 over 1, or I could do 9 over 3 or whatever. So that's not a problem. Obviously, the number 1/2, well, it is, in fact, a fraction. It's already in a fractional form. So I don't need to convert it. It works, and so does 3. Now, what an irrational number will do to us is we need to look at numbers that don't fit that form. The number pi is 3.141592 blah 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 blah, and it goes on forever. What's special about the number pi is it is irrational. It doesn't repeat. We can't make it into a fraction, because in order for a fraction to write a number as a fraction, the digits eventually have to repeat, or they have to end, they have to terminate. Pi doesn't terminate. Because pi doesn't terminate, we classify it as an irrational number. So it can't be written as a fraction. Okay? Why that's important for where we're going is because we're going to radicals. And again, any number that we write using a radical sign is, by definition, a radical number. Like radical, brah. So the square root of 36, when it's written in that form, is in fact a radical. Now, if I simplify that, I mean, obviously I'm hoping everyone's looking at that and going, Stoltz, why would you ever write that as square root of 36? That is actually just 6, because what a radical asks us every single time is what two numbers, when I multiply them together, what number, when I multiply it by itself, equals the number under the radical? Well, 6 times 6 is 36. That's where that comes from. This is a rational radical because it can be written as a rational number. The majority of radicals are not rational. Instead, the majority of radicals are irrational, and an irrational radical is what we call a surd. So the square root of 3, that is an irrational radical. There is not a way for me to write that down. I bet you my calculator, even if I try that and do square root of 3, I'm going to have to do approximately equal to, it gives me this number. Now again, that is an estimate. I've just asked my computer to write it again, and you notice it rounded after this 5. There's still more. And the thing about it is it'll keep going. It is just like pi. It won't terminate. It won't start repeating itself. It's irrational. So that is what a surd is. It's an irrational radical number. And basically, if it ain't a perfect square underneath the radical, it's a surd. Okay? Now, that's kind of a little short little bit, like that's kind of nice to recognize. But what we want to be able to do with radical expressions and radical numbers is we want to be able to manipulate them algebraically. And for that, we need a couple of rules. One of these rules we've actually already seen. This rule here, where we did this, I think, in the past, you've done this to prove that a to the 1/2 power times a to the 1/2 power is in fact a. Well, what that's doing, when we multiply them, it works out that that's what's happening. So the reason we can do this is if we multiply two radicals that have the exact same number on the inside, we'll just get the original number. What's more important after that are these next two rules. We can also work with a radical, do something like the square root of 3 times the square root of 5. Well, if we're multiplying, only if we're multiplying, we can just multiply under the radical, okay? So what this would turn into is the square root of 3 times 5, which would just be the square root of 15, okay? So that's a rule, something we got to know, got to be able to get it. Similarly, and it's funny because the rule shows it like this going to there. I normally think of it the other way because that's normally how it comes up. But if I have the square root of 5 divided by 7, I would end up with the square root of 5 over the square root of 7. Those are equivalent statements. Now, yes, this is the simplified. That's the simplified form. But the reason why I say this is important, because a lot of times what happens sometimes when we're dealing with Pythagoras and some other things that ask us to take the square root at the end, is if we ended up with something like the square root of 16 over 5. Like technically, actually, let me not do that so I just don't get into a problem right off the bat that we have to deal with. If I did that, I could actually rewrite that as the square root of 5 over the square root of 16. Well, the square root of 5 is a surd. We can't do anything with it. The square root of 16, I could rewrite that as square root of 5 divided by 4. So that's a really important rule. If you see it, we can simplify taking the square root of either the top or the bottom. Sometimes you can take the square root of both. Not often, though. Okay. Now, all right. Something crazy just happened. I had to answer a phone call, so I'm back, and we're going to keep going. So, crazy jump cut. So, what I said is we need to be able to we need to, often we're asked to take a radical and turn it into simplest form. So, I think the best way of looking at how we do this is by just taking an example. The square root of 32. First off, we know right away it's a surd because it's not one of our powers that we know. 5 squared is 25, 6 squared is 36. This is somewhere in between those two. So what we need to be able to do is we need to be able to figure out what I can divide out of there, what we can bring out. So what I'm going to do is I'm going to factor this. I'm actually going to go ahead and use a prime factorization method like we've definitely done in the past, where I'm going to take 32 and I'm going to divide it by prime factors. I know 32 is divisible by 2, which would give me 16. I'm going to divide that by 2 again, and it would give me 8. Still good there with another 2, right? And that would give me 4, and then 2, and then the candle on top. We're good there. So I'm going to rewrite the square root of 32 as 2 times 2 times 2 times 2 times 2, 2 to the 5th. What this does is anytime, now we're going to pair them up. Okay, well 2 times 2 is 4, which is the square root of 4. is 2. So every time I have a double under there, I can pull one out. So I've got one double, I've got two doubles, and I'm left with one that's going to be stuck underneath the radical. So if I do this, I would have a 2 on the inside, and then I would have multiplied by 2 times 2. So this is actually 4 square roots of 2. All right, so I factor it down. Now, we can use prime factorization to do this. It's not always the most efficient way. I think if you looked at this, you could recognize that this is 4 times 8, so, or 16 times 2. And 16, dividing that out, would the square root of 16 is 4, so that would pop that 4 out right away. That is where we want to get to. Where we need to start at is accuracy in getting there. So a lot of times the prime factorization method is how we do that. Just to confirm, if I take my calculator, I need to delete some things, and then I need to go control square root of 32, and then I'm going to do 4 times the square root of 2, and my calculator is just simplifying it to that. But now we can see, because it's simplified it for me, it's 4 square roots of 2. I want to do one more example, and then I'm gonna cut you loose on this one to go try some problems, because that's what we need to be doing here. Let's try the square root, I don't know, let's do of 90. Okay, square root of 90. Let's think about how we can divide that. Let's think what we can take out. One of the fast ways of doing this is look for perfect squares. What can I take out? Well, I already know I could rewrite this just as 9 times 10. 9 is already a perfect square, right? 9 is 3 times 3. 10 I can't do anything with. So the fast way of doing this, which would get me my correct answer, 3 square roots of 10, would be figure out what we can multiply together and then pull things out. Notice this also works if we use prime factorization. Prime factorization of 90, if I start with 3, I would end up with 30 here, and then I do 3 again, and I would end up with 10, and this is 2 and 5. Square root of 3 times 2 times 5. There's my pair. I can pull a 3 out. I don't have any more pairs, so I'd be left with 3 square roots of 10. Both ways work. Both ways are completely correct and efficient. Well, prime factorization always works. It's not always the most efficient way. But there we go. Hope that's helpful.